when we started talking about conditional probability, that when two events E and F are dependent, then the conditional probability formula for them can take either of these two forms. Either we can write probability of E given F is equal to this side, which is probability of E intersection F, that's when those two events happen at the same time, divided by probability of the known event, the one that has already occurred, which in this case is the event F. If we swap these, if probability of E and F are swapped, if instead we have probability of F given E, then the intersection probability is divided by the other known probability, which is in this case it's event E. So that divided by probability of event E, which is the given event. Again, I cannot emphasize more, this is for dependent events. But what happens when E and F are independent? Can we use these formulas? No. We still have conditional probability formula, we still use that, but the formula on the right-hand side is not the same thing. So let's see how these things simplify. So if E and F are independent, then probability of E given F for events that have absolutely nothing to do with each other is equal to probability of E. Because E and F have nothing to do with each other. E may have something to do with another event, but it has nothing to do with F. So probability of E given F, if E and F are independent, then is equal to probability of E, whatever it is, right? By the same token, probability of F given E is equal to probability of F. Okay, these are two of the three most important formulas about independent events. The third one is actually much more important than these two. And that is that if two events are independent, then probability of their intersection, probability of E intersection F, is equal to the product of their individual probabilities. This is extremely important formula, but people misuse it or use it in an incorrect situation because they use this with dependent events. No, this is for independent events. You can use this formula only if the events are independent. Independent events only. By the same token, if we have three events that are independent, we can say, let me write that here. If we have three events, E, F, and G, that are independent, then we can say that probability of E intersection F intersection G is equal to probability of E times probability of F times probability of G. So when do we know if events are independent? We might be told that directly or explicitly, that events assume that events E and F are independent, or we may have to deduce that from a situation that is set up for us in a word problem in those two cases. For example, in a situation where you have a basketball player who's shooting 2 shots from the free throw line, right? If we know that the probability of him making it on each shot is, say, 89%, then we can say, okay, what's the probability that he will make both of his shots? In that case, we will say that's the two shots are independent of one another, because if he misses one, the first one, it's no guarantee that he'll miss the second. Or if he makes the first shot, there's no guarantee that he will make the second shot as well. So in that case, from the context of a word problem, you can think about it and decide whether the events that are being discussed are dependent or independent. Also, sometimes problems make it easy and tell us that assume that such and such events are independent, in which case we can use these formulas. Okay, so having said that, let's look at some examples. So if E and F are independent, find probability of E intersection F. Okay, so here we are told explicitly, right, that E and F are independent, and if probability of E is this and F is that, find probability of E and F. Okay, because of this, then this is equal to probability of E times probability of F, right? So probability of E intersection F then would be 0.4 times 0.6 or 0.24 and carried to 2 decimal places. Okay, so that was just to get us to use that formula once. Let's look at other examples. If E and F are independent, we want to find probability of event F if probability of E equals 0.2 and probability of E union F is equal to 0.3. Okay, so the notations here speak to us, right? This notation, where have we seen this before? We've seen this with the additive rule. So as soon as you make that connection, write the formula down. So probability of E union F is equal to probability of E plus probability of F minus probability of E intersection F, right? We know that from previous videos. Okay, so let's plug in for the information we have and solve for the information we don't have. So we have E union F, probability of that is 0.3 equals probability of E, which is 0.2, plus probability of F. Well, we don't have that. We're looking for it. So let me keep it as it is. Probability of F minus probability of E intersection F. So that's another quantity that we don't have, right? We don't have that information anywhere. So let's write that down as it is. Probability of E intersection F. Well, here, if probability of F was the only unknown case, we could solve for it easily. But here we have two unknowns. this piece is unknown, this piece is unknown. In a single equation, we have two unknowns in one equation. So if we didn't have additional clues, we couldn't solve this equation like this. But fortunately, we have additional clues, right? It says that E and F are independent. That's a very important clue, because if E and F are independent, then probability of E intersection F can be written as probability of E times probability of event F, right? We know that for independent events. So let's substitute in this equation with its equivalent. Therefore, so we write down 0.3 equals 0.2 plus probability of F minus, instead of that, I'm going to replace this piece with its equivalent, which is probability of E times F. Probability of E times probability of F. Right? Great. So now we have probability of E, we can substitute for it, and then we'll end up with an equation with only probability of F missing, which we can easily solve for it. So let's do that. 0.3 equals 0.2 plus probability of event F minus, let's substitute for probability of E with the number 0.2 times probability of F. Right? Okay, so here is where a lot of people have questions. So how do we combine this? Well, think about it. Think about how to combine these. This is easy, right? If you think of this problem as, instead of probability of F, imagine this probability of F was just X. Imagine if you had X minus 0.2X. How would you combine those? This is no different than that. So we can quickly write, this is 1 probability of F minus 0.2 probability of F. So we have 0.8, right? 1 is the coefficient here, minus 0.2, that's 0.8 probability of F. So now we can easily solve for the unknown quantity, which is probability of F. So we have 0.3 minus 0.2 equals 0.8 times probability of F. Let me move over here. And then we have 0.1 on the left-hand side equals 0.8 probability of F. And so probability of F is equal to 0.1 over 0.8, which is, let's see, it is 0.125. 0.125, and which is what we wanted to find out. Okay, so this is an example of how these formulas that we're learning about can work together. In this case, additive rule, which we had talked about sections ago, can be used with one of these formulas that we have for independent events. Okay, so let's do one more example using conditional probability for dependent events. So suppose So here we have one of those data tables or frequency tables. So we have this, we have, let's see, we have 1, 2, 3, and then we have 1, 2. Okay, so here we have the type of residence. And this is urban, suburban, and rural. And of course, this bottom row is total. Again, if this total row or total column is not given to you, you should calculate it. Okay. And here the topping is burglary. Then we have vehicle theft. Then we have theft. Okay, and here are the frequencies: 44, 14, and the totals. Well, we have the column there, and then here we have 100, 28, 372, and 500, which is the grand total. Okay, so given this frequency table, we are asked to answer some question. So this is frequency tables. These are dependent events. I'm just adding this example in addition to the example that you saw about one of these frequency tables in the previous section, 8.1, which was about conditional probability. So, but the three formulas we have for independent events do not apply to this example. Okay, so we want to know Okay, so suppose this is the question we're trying to answer. Let's convert this to notation and then we'll answer it. I hope you pause the video, do answer this question on your own, and then look at my solution. All right, so I'm assuming you've done that. You already have an answer for this part, and you're ready to see my solution. So probability that the residence is rural, given that there has been a vehicle theft. Okay, so that's the question for us to answer. We can complete the conditional probability formula for this by writing probability that a vehicle theft has occurred in a rural area according to this data, divided by any vehicle theft, probability of any vehicle theft according to this 500 data points. Okay, so that's the completed formula. Let's plug in numbers here or here. We want to first look at all those events all that include a vehicle theft in a rural area, right? Both of these, that's the symbol for that both of these are happening. So vehicle theft in a rural area. Rural area, vehicle theft, there's only 4 of those. Okay, so 4 out of 500 divided by probability of vehicle theft anywhere, right? So vehicle theft anywhere for all areas was 28. So 28 divided by 500. 500s cancel out. We have 4 over 28, which is 0.1429. The answer is carried out to 4 decimal places. Okay, so let's ask another question for this data. Let's call that part B. We want to know what is the probability of being burglarized given the residence is suburban. Okay, please pause the video, write down your own solution, and then come back to the rest of this video. So I'm assuming you've done that. So the probability that of being burglarized given that the residence is suburban. So that's the question before us. And let's complete the formula. Probability of being burglarized in a suburban area divided by probability of being a victim of crime in a suburban area. All right? Okay, so let me scroll this down so we can look at what does the data say about the number of crimes that happen, burglary crimes that happened in a suburban area. So, right, with both of those conditions being true. So, burglaries in suburban areas, there was 30 of those, 30 out of 500, right? So we have 30 out of 500 divided by probability of any of these crimes having occurred in a suburban area. So that would be, for all crimes in suburban area, we had 146 of those. So 146 divided by 500. Okay, so the 500s cancel out. We end up with 30 divided by 146, and that is, the answer is 0.205 carried out to 3 decimal places. Okay, so this is a problem that initially we introduced in section 7.5. We had a couple of examples in that section that we went over. I thought it's nice to bring it back again in this section because, first of all, it has to do with the concept of independent events, which is very much related to the topic in this section. And also, it's an important type of an example. In probability and statistics, you see quite often you see examples like this. So it's good that we spend a little more time on examples like this. So we have here a cold medicine that apparently it's 97% effective in eliminating cold symptoms. So 2 co-workers, so these are all important clues in the problem. We have only 2. So 2 co-workers that have been experiencing cold symptoms and take the cold medicine, and assuming that the effect of the medicine on one individual is independent of its effect on another individual, then we have to answer this question. So what is the probability that both co-workers' cold symptoms are eliminated after taking the cold medicine? So it's really helpful if you think of these words and translate them into symbolic form in this context. So both, let's introduce some variables first of all in order to begin to solve this. So I will just say that I'll just pick, you can choose any other variable, but I'll just use P1 as, and I'll define this as the event that, so person 1, let's say person 1 or individual 1 experiencing the elimination of the cold symptoms, and I'll say P2 for person number 2 experiencing the elimination of the cold symptoms. Okay, that's the first step in solving any kind of word problem, because you need to introduce variables. They're not given, so we have to introduce them. So we just did that. The next thing is, as I said earlier, is try to come up with a symbolic interpretation of these words that you see in the problem. So in this case, the word both translates, and notice the word probability also, probability that both, in effect, we are being asked to calculate this probability that the first individual, or the person 1, and this both means this individual and that individual, right? So that translates into this notation. Probability that person 1 and person 2, that means both co-workers, are experiencing the elimination of the cold symptoms. So fortunately here we have a word that is an important clue about this problem, which is that the effect of the medicine on each individual is independent of its effect on the next person who takes the medicine, right? So because of that, because that is independent, we're dealing with independent events, therefore we can write that, translate that symbolically and say that this is, that quantity can be written as probability of P1 times probability of P2. Only because, I don't know how, it's impossible to overemphasize this, but I want to maybe, if I draw an arrow from that independent to that, it's pretty critical, because I've seen people use this when events are not independent, and we cannot do that. We cannot use this formula only because it's convenient to do it, to use it. Okay? In this case, fortunately, we can. Okay, so we know that the effect, the probability that this individual feels relief from cold symptoms is 0.97 or 97%, right? 97%, that is 0.97. And times the same probability for the next person who takes it, right? So then the probability that both of them feel relief from the cold symptoms would be the product of those two probabilities or quantities. So let's do that here. So we have 0.97 times 0.97, and we get that quantity. So 0.9409. Usually I'd like to keep or round my final answer in this topic, probability, to 4 decimal places. In this case, we don't need to round the number because it's already stops at 4 decimal places. Okay, so that's that. Then the next question for us, or the next question we can ask, is what is the probability that at least one of the co-workers experiences this relief from the cold symptoms? So what is okay? All right, so here, the key phrase that has the clue for how to solve this problem is right here, at least. So in this context, probability calculations, we can translate that phrase at least to the union of events. So probability of P1 union person, the second person. At least means one of them, right? At least one. So that means if individual 1 experiences relief but individual 2 doesn't, then plus individual 2 feels relief and individual 1 doesn't, and minus the probability that both of them experience pain relief. We subtract the both case, the probability that both feel relief from the symptoms, because as we mentioned earlier, when there's an overlap of probabilities, then we need to subtract it once in order to prevent duplicating probabilities. So this union, in effect, has this formula, as you remember, as the additive rule. That is equal to that, probability of individual 1 experiencing relief, probability that individual 2 experiences relief, minus probability that both of them feel relief from the symptoms. Okay, so here we saw that there is an overlap because these are independent events. So there is an overlap that both can experience symptom relief from the symptoms. So if we add those two individuals' relief, probability of relief from the symptoms, then we must, within that, there is already that included, the overlapping piece. So we need to subtract it once. So we're subtracting that quantity once. Okay, so it's important here to connect that phrase to the union symbol. And the union symbol, we know the additive rule is the formula we can use. So all we should do now is just plug in for these quantities. So 0.97, 0.97, minus, of course, both feeling relief from the symptoms, which we already calculated in part A. So 0.9409. Okay. So if we calculate this quantity, let's see if I can include everything on the screen here. Yeah, I can do that. Okay, so 0.97 plus 0.97, 1.94, right? And then minus that, minus 0.9409, and we have 0.9991. Okay, like that. So this is the probability that at least one of the coworkers feels relief from cold symptoms. So let's add another part to this and ask, what's the probability that neither one feels any relief from these symptoms? So let's call that part C. Okay, so what is the probability neither coworker from the symptoms. So there are two ways you can use to answer this question. Both ways are valid ways, and I'll talk about both ways. So one solution is this: to realize that neither coworker feeling relief from the symptoms is actually the complement of the union case. So this one, part B, what is the probability that at least one coworker feels relief from the cold symptoms? So either this person or that person or both feeling relief from the cold symptom. That's that. So what is the complement of this? Complement of this is, of course, neither one feels any relief from the cold symptoms. So using that understanding, so realizing that is the complement of at least one coworker feeling relief from the symptoms, then we can write this. We can say that probability, so neither coworker, so that would be this, we can write it as probability that the first individual union this at least complement, and I'll put this bar in red so it stands out. So that is what this question is really asking about, the complement of the at least case. Okay, at least means either this or that or both. Neither means neither, right? Exactly complement of at least. Okay, so that makes it really easy to answer this question, because we know that any complementary events, their probabilities should add up to 1. So therefore, we can write 1 minus probability of P1 union P2. So that's why I encourage you as you solve these problems, think of them in terms of symbols before you plug in numbers. That way you understand how these problems are solved much better, and you'll have a much easier time of remembering these later. Okay, so that's what it means symbolically when two events are complementary. Okay, so now the easy part is just plugging numbers. So 1 minus what we ended up with for the at least case, which was 0.9991, right? So let's plug that in, 0.9991, and that gives us this result, or 0.0009. So it's a very, given this probability that this medicine is effective, then it's highly unlikely that neither one experiences any relief from the symptoms after taking this medicine. Okay, so I said there's two solutions that you can use, and you're welcome to use either way. If one way makes more sense to you than the other one, you can do that. So second solution would be this. So we know that the medicine is 97% effective, right? Okay, so we know what's the percentage that it's not effective. Okay, so let's find that out. So therefore, from this result, we can say that that's probability that medicine is not effective is simply 1 minus 0.97 or 0.03, right? So if both people experience no effect from taking this medicine, then thus from the symptoms, because the effects are independent of each other, then we can write that probability that one person experiences no effect times probability that the second individual experiences no effect. So I'm taking the bar on top. Of course, you remember it refers to the complement of an event. So remember that P1 was we labeled this as a person one experiencing the elimination of the cold symptoms. So P1 bar, like that, means that person one does not experience any relief from the symptoms. And because these are independent from individual to individual, we can multiply them together. We can get 0.03 times 0.03, right? That's when the medicine is not effective. And therefore, we get 0.009 again, okay, which is what we had up here, right? So we have that up there. Okay, so it's two solutions same result, and I encourage you to pick one that makes more sense to you. All right, so let's look at another example of a different type. So suppose events A and B are independent, and probability of A is equal to 0.29, probability of B is equal to 0.34, then find so that, and then we want to find probability of A given B. Okay, so recall that we said, I haven't been reminding you, but it's nice if you pause the video and just solve this problem on your own and then come back to the video. That way I'm sure you learn most from going through these examples like this. Okay, so recall that when two events are independent, like A and B in this case, then probability of A given B is simply equal to probability of A, right? For independent events, of course. Okay, so we really don't need to calculate anything here, because we can right away notice that probability of, remembering that for independent events, then we can easily say that probability of A given B is simply equal to probability of A, or 0.29. Okay? And of course, if the question was asking for probability of B given A, if that was the question, then the answer, of course, would be probability of B, right? Because B and A have not, if they're independent of one another, then they have nothing to do with each other. So calculating probability of B given A is just probability of B again, with no regards to probability of A, because the two events have nothing to do with each other. Therefore, probability of B given A would simply be equal to probability of B. Okay, like that. Okay, so let's look at another example. So if we have probability of A is equal to 0.58, right? Probability of B equals 0.23. And probability of A union B is equal to 0.76. Find probability of A given B. Okay? So suppose we have that question. All right, so the first thing we should look at is write the full formula for conditional probability of A given B, because that's the question, right? So let's go straight to this formula for calculating this quantity. That would be probability of A given B we know it is equal to probability of A intersection B over probability of B, right? Remember that from conditional probability formula, right? So now we have probability of B given to us, fine, but probability of A intersection B is not given, right? So how do we calculate this? Let me use a scratch paper here just to make a point. Would you use, let me ask you this as you watch this video. Question for you is, would you use, let me move this up a little bit. So, would you use probability of A intersection B is equal to probability of A times probability of B? Would you use this formula to obtain probability of A intersection B? Would you do that? Would you? I mean, you're sitting at home watching this. Would you do that? It's not given. Would you use this formula to calculate that? Because probability of A is given, probability of B is given. Why wouldn't you use that? Why wouldn't you multiply those two quantities to calculate this? The answer is that you should not use this formula in this case. So we cannot use this formula to find what probability of A intersection B is. Okay? Why not? Well, note that we cannot use this formula to find probability of A intersection B because we are not told that A and B are independent. See, before we were told that A and B are independent, right? We were told that. So, well, that's not the example I want to look at. Let's bring one of those back from previously. So here, I mean, in looking at the problem where it was talking about medicine, right? The effectiveness or lack of effectiveness of this medicine was independent from individual to individual. So we could multiply probabilities when it was not effective. We could multiply probabilities when it was effective. But here, we're not told that. Nowhere here says that A and B are independent, so therefore we cannot use this formula. Okay, we cannot use it. To find, and let me complete this, because A and B are not independent in this case. Okay? All right, so what else can we do? Well, there's another piece of information we are given, which is very, very helpful, and that's this union. What does this symbol remind you of? What does this symbol remind you of? Remember that? The formula, the additive rule? So let's write that down. So we know that probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. And in this formula, do we have probability of A? We do. Do we have probability of B? We do. Do we have probability of A union B? We do. So in this formula, out of all these four terms, this one, which is the one we're looking for to use with this conditional probability formula, is the only term missing. So we can plug in for these and solve for the one that is unknown. Okay? So let's use the additive rule in this case. Okay, so plugging in, we have so 0.76 equals probability of A, which is 0.58, plus probability of B, which is 0.23, right? Those quantities are up there. And minus probability of A intersection B. So simply move this term, this one term to the left, move 0.76 to the right hand side, and we will have probability of A intersection B is equal to 0.58 plus 0.23 minus 0.76, right? We're solving for this term. So therefore, we have from this, what do we have? We have probability of A intersection B. Just adding and subtracting these terms, I have 0.05. And let me double check my number here. So 0.58. 0.58 plus 0.23 minus 0.76, and we have 0.05. Okay, so now is the time for us to use this quantity in this formula. Right? So we plug in. We say that probability of A given B is equal to, move this up a little bit, like that. That's equal to probability of A intersection B. We just found that using the additive rule divided by probability of B, which was 0.23. So what do we get? Let's calculate that. So we have 0.05 divided by 0.23. We get that number, right? So let me write that down, 0.217391304. Normally in probability, usually or most often, we would want to round this to 4 decimal places. So this would be 0.217, and then 3 should be rounded up, because the number that comes after it is 5 or higher. So if it was 5, 6, 7, 8, 9, we would round this up. So this would be 4. And so we have our answer rounded up to 4 decimal places. Okay, so that's that. Let's do one more example. So let me enter an intern as, well, not there, I meant to put that, as a regular employee, okay? All right, so we have a scenario here where we have a technology firm that hires only 20% of its summer hire interns as regular employees. Knowing that the company's decision to hire one summer intern as a regular employee is independent, these are important clues, right? That is an important number or quantity. This is an important clue. And finally, in the question itself, the word both is a very important part of that question. So if the decision-making process is independent from individual to individual, then we can surely use the formula for that, right? So, but let me introduce label here for the variables we're going to use. So I'm going to say I for intern, so intern 1 would be the event, so I pick that variable. You can use X or Y, you can use AB, you can use EF, you can use whatever variable that makes sense to you. But I'll use intern 1, that variable represents the event that that one summer intern is hired as a regular employee. Okay, and let's do the same thing, but I2 meaning the same thing, the event that the second summer intern, right, is hired as a regular employee. Okay, so now that we introduced the variables and we know that this decision-making process, we are told that it's independent from intern to intern, so we can then use, let me bring that here, we can say that probability that both of them, this is the question they're asking, intern 1 and intern 2 are hired as a regular employee would be equal to probability of intern 1 times probability of intern 2 being hired as a regular employee, right? So we know that's 20%, this is 20%, so this would be 0.2 times 0.2, and what do we have? We have 0.04, right? That's the probability that both of them get hired after the after the internship as a regular employee. So 0.2 times 0.2, we have 0.04. Okay, so part B, let's ask, what is the probability? I'm sure you've already guessed what part B is going to ask about. So what is the probability that at least, right, at least one of the two interns is hired as a regular employee? Okay, again, that phrase refers to the union of events. Remember that? So at least is referring to the union. All right, probability of intern 1 union, probability that intern 2 is hired as a regular employee. And of course, this is reminds us of the additive rule, right? Probability of intern 1 being hired as a regular employee plus probability of intern 2 being hired as a regular employee minus probability of intern 1 intersection intern 2. Okay, all right, so let's calculate this quantity. This would be 0.2 and then plus again 0.2 minus this quantity, which we already calculated in part A for both being hired. So that would be minus 0.04. And then, of course, add these, subtract that, you get 0.36. Okay, so that's the probability of at least one of the two interns being hired as a regular employee. Either this guy or that guy, or not this guy but that guy, or both, right? That's what this is calculating. And part C, let's ask about the probability of neither one being hired as a regular employee. Okay, economic conditions, whatever, they're downsizing, could be all kinds of reasons, right? So what is the probability that neither summer intern is hired as a regular employee? Okay, so we have, that is of course the complement of part B. So we have neither summer intern, that, so both of them are not hired, so that is the complement of part B. So this would be probability that intern 1 union intern 2 and then complement of that. Okay, so that's what they're asking us here about, and we know that any event and its complement are connected, as the probability of the complementary events should add up to 1. So this would be 1 minus probability of that and union I2. So 1 minus 0.36, and that's 0.64. Okay, so I hope this was helpful in helping you make sense out of the concept of independence of events and their probabilities. And thank you again for persisting through this video. And this is going to wrap up section 8.2. So for now, have a nice day, and I'll see you again next time.